news. I know we're a couple minutes early, but it's going to take me a moment to introduce Pedram Amini anyway. So there's a lot to talk about. If you haven't heard of Pedram, you probably have utilized a tool that he's written or been involved in something like a vulnerability disclosure program, but he's currently the CTO at Inquest. He previously is at a number of startups and currently lives in Austin, Texas. He is one of the founding members of iDefense Labs from way back, and then it got acquired, I think, by, it was VeriSign first and then Accenture after that. But he's one of the founding members of that, and then went on to start up the Zero Day initiative back early on under Tipping Point. So ZDI and iDefense both started by Pedram. So one of the early on pioneers of the whole world of vulnerability contributor programs and making sure that people get paid for that. You know, thousands of researchers submitting bugs which end up getting disclosed to Microsoft and other organizations as they're affected. So when I think of like one of the people who started up the whole world of getting paid for your security research and bug bounties, I think of Pedram. He's spoken at Black Hat, DEF CON, ShmooCon, I think Echo Party, many different conferences out there. He's taught courses on reverse engineering. He's a huge contributor to the security community. He wrote the Sully fuzzing framework, which we still actually use a bit in 660, which of course is a forked version, which is BooFuzz, but Sully was Pedram's work. Also, the PyMay and PyDebug, if you've used those reverse engineering frameworks, he's the author of those. We've got just so many more tools, but his talk is titled Identifying Novel Malware at Scale. When I first glanced at it, I'm like, novel malware, like, oh no, not novel malware, novel malware. So with that being said, I know we're a couple minutes early, but I'm sure he's got a lot to say. So let me introduce Pedram Amini.
Thank you, Stephen, very much for that. How is audio, video quality all good?
Yep, it's great.
Great. Really appreciate the introduction. You've got me blushing. Very, very kind of you. I'm happy to get started. Let me see if we've got mouse control. There we go. So Steve gave a great introduction, really covered my entire background. Predominantly historically, I've been very interested in, the minutia of deep like vulnerability development, exploitation. And today I find myself, more focused on large scale. So, dealing with millions upon millions of samples a day. How do you determine which ones of those samples are the ones that you should be focusing your efforts on? And that's really the subject matter of this talk, is kind of walking through large scale data sets and talking about, what's working for attackers, what's working for defenders, and, what we do internally, at least at Inquest, for, managing this problem with scale. So, one of my unfair advantages, as I like to call it, is, I've gotten to work with thousands of researchers globally. I've seen countless zero-day in my time at iDefense's VCP, and since starting the Tipping Point as zero-day initiative. But although there are some really beautiful exploits out there, you look at like works of truly like art, like things like Stuxnet, or some of these jailbreaks, or thinking back to like Pinkie Pie's, like 18 chained vulnerabilities to get to pop a shell on Chrome. There's a lot of beautiful exploits out there, but if you look at what's actually working for attackers, like what is resulting in folks getting owned, it's really quite simple stuff. It's low-hanging fruit. It's your invoice scams, it's your phishing attempts, right? It's open S3 buckets and open Elastic databases. And the last one is carrier lures, right? And so carrier lures are a just generic term for, all your client-side application, like document type providers. So like your Microsoft Office documents and spreadsheets, your Adobe PDF files, things like even like scripts and archives, Java applets, Flash applets, which, to a large degree, Flash is dead today. Most of the browsers are blocking it, but the subsystem is still alive and well and reachable for many folks. And you don't have to look back too far. In 2018, there was a zero-day found in the wild, attribution-wise, that was credited towards the North Koreans launching it towards the South Korea. So carrier lures is the part that we focus a lot of attention on, and where I'm going to be focusing this talk. So, let's look at it as, from an attacker's perspective, what's the formula for success? If we were going to turn around tomorrow and start our own malware campaign operation, it starts with, if we're looking at it from the carrier perspective, we're going to construct some novel carrier. And the exploit is optional. It does not have to exploit some 0-day or some end day. We can very happily embed some logic like a macro into a document and email it out to a number of potential targets. And somewhere, one of those users are going to open up our attachment, and we're going to get a foothold onto their system that we can then start pivoting from there. Once we've gotten a novel carrier, we're going to want to do some testing on it, right? So you'll throw it up against a virus total, or if you've got some private instance where you've installed a bunch of AV technologies, you want to ensure that your carrier is going to be stealthy enough that it's going to, between the time of releasing your campaign and when it's actually going to be caught and defended against, you're going to harvest a good amount of targets. The next step is, either you need to own by purchasing or you need to pwn by taking over, or you can utilize some shared infrastructure like your GitHubs and paste bins and Slacks, and I've even seen some command and control and pivot activity happen on Twitter. Once you've gotten all this stuff put together, you seed your campaign via some spam, and now it's profit for the attacker. And we don't have to look very far to see the success of this, right? These columns are the top 10 most exploited CVEs per year. They're in alphanumeric lexicographical order, so not in the order of popularity. The legend across the bottom, so you'll see Flash, PDF, Android, Java, IE, Office, and Windows. And 2018 and 2020 comes from Recorded Future. That 2019 table comes from US CERT. Look at that; it's almost entirely Office or Office related, OLE related, even at that. That Flash vulnerability, that 0-day that I talked about from 2018, there it is highlighted in red. So this 2018 4878. The bolded ones here are the ones that are the most common. So this 2017 CVEs 0199 and 11882. The reds are 0 days that were found in the wild. So these are cases where defenders saw this being exploited in the wild, and they in turn reacted to it, building defenses, creating patches and whatnot. What's really interesting, and this is the subject matter of my Black Hat talk last year called Worm Charming, is in all of these cases, you had between a week and 2 weeks of lead time prior to the campaign really taking off, where those samples and that 0-day was sitting in virus total. There's another group of guys from Eurocom and Symantec that did a talk called Finding Needles in Haystacks that's more related to portable executable malware discovery. And I mentioned, no exploit is required. So outside of all those CVEs being the top exploited per year, almost all of them falling on the Windows desktop side of the spectrum. Here's one that's eating everybody's lunch at the moment. It's an old technology. This is Microsoft Excel macro sheets were introduced in 1992. Right, and this technique, we found it somewhere in January of last year. An initial iteration of it where folks are embedding this old version of Excel macro sheets. It's a different way of getting embedded logic into a spreadsheet carrier, and over time, it just started picking up in popularity. Today, we're actively tracking this as being the most commonly stealthy and bypassing a tactic, and it's completely exploit free. One of my colleagues, Amir, known as Dissect Malware on Twitter, he wrote this tool called the XLM Macro Deobfuscator. It's free and open source. I would highly recommend that in terms of using it for dissection purposes. I'll drop these links to the blogs for any kind of samples if folks are interested in it. And we have a series of Yara rules as well that can help you in your either threat hunting or defensive operations. If you're interested in more specifics on maldocs, I would recommend Didier Stevens' talk from yesterday. Didier is really well known. I have a lot of admiration for the work he does. I use his tooling daily. He wrote tools like OLE dump for walking the structured format of these pre-2007 compound document format files. And in his talk, he jumps into a bunch of more specifics on payloads and getting them past defensive mechanisms. He also disclosed a couple of new ways of new tactics, the most interesting of which is a code signing tampering bug. Not to just real synopsis, in essence, there's two types of code in your embedded VBA, and the one that's signed, you can modify the compiled version of the P code version of it and essentially bypass the signature check. Really, really neat tech. For sure, you're going to see this being exploited by attackers in the not so distant future. Zooming out and looking at a common malware campaign, kind of like a visualization of what we covered in the beginning, the 3 steps for an attacker to profit. What it looks like when it comes to your users is typically it's going to be delivered over email, whether it's an attachment or a URL, phishing, whatever it is. Something like 90-something% of attacks are email born. It doesn't matter who you ask; they all have some number that's over 90%. So that's the initial opportunity, the initial interaction with these malware campaigns. From there, typically most malware is multi-stage. Whether it's pivoting through some living off the land technique, PowerShell in Windows, maybe like a Python and a Mac OS. Typically there's multiple layers to a successful exploited system. Maybe it'll make an HTTP request to, for example, a compromised WordPress site. This is something that we'll see fairly commonly. You'll see malware hosted in some random restaurant in Greece because unfortunately that guy was running an old version of WordPress, and some spray and pray campaign guy went and picked that up and added it to his list of infrastructure for places to host his second stage payloads. The benefit of this, of course, is he didn't have to stand up the infrastructure. So tracking wise, if you're doing actor tracking, you might not be able to catch this new node that he popped. And also it's got good reputation. That poor restaurant in Greece, for example, has been around for years. It's a legitimate website. And so he's piggybacking off of that rep. Another option, of course, is to communicate with your own stood up malicious servers. More commonly, folks are using US-based IP addresses, standing up temporary services and hosting providers like Amazon, just as one example. And finally, you've got your final like payload delivery. So when we're looking at the malware campaign from a defender's perspective, there's a number of different places here that we can provide defense. We could, at step 1, maybe block that email. At step 2, perhaps we can detect the traffic pattern or detect the URL structure of that compromised website. Maybe we can, at step 3, we can identify the attacker's infrastructure. We're tracking IPs, domains. These are pretty standard IOCs. And more popularly, we're tracking SSL certificates. So you can look at like your JA3 or JA3S hashes from the folks over at Salesforce. And commonly what defenders are doing is once they've got an anchor on attacker infrastructure, they start to pivot. So for example, if I have a known bad domain name, I can go look at what IP address that maps to, and then go do a reverse IP lookup and see in turn what other domain names are hosted on that IP. That's not guaranteed, of course, to give you other bad domains. It's very possible they're in a co-hosting environment, but it's one tactic. There's to go from the domain name to the DNS server and see what other domain names that DNS server is authorized to answer questions for. Perhaps there's a pattern in the domain name and you can do a pivot on that. You look at the registrant, you can brute force subdomains. IPs can go to ASNs and you can pivot from there. The bottom line is that from each one of these different anchors, whatever we're given, we can start mixing and matching and kind of expanding out our scope and knowledge of the infrastructure. I had mentioned SSL certificates. Another common one that we're using is Google Analytics IDs. Funny enough, malware campaign authors want to track their campaigns, and they'll use things like Google Analytics. And so if they're going to go ahead and put that anchor in there, why not leverage it to enumerate the rest of their infrastructure as well. If you're curious on doing some free open pivots, and these slides will be posted, don't worry about copy pasting and whatnot. Here are some places you can do that. Some tooling that's open and can be used for pivoting and enriching IP addresses. Later, we'll also talk about Inquest Labs. It's an open data research portal. You can get some IP and domain name pivots from there as well. The other kind of pivoting that we can do, and this is something that is more in tune with my daily research and interests, is we can pivot on the file itself as well. And one of the first things that we do when we're processing files is we extrude them, right? Very, very common that these malware carriers are encapsulated. So take that flash 0 day, for example. If that flash 0 day was inside of a Word document, that Word document was zipped, that thing was emailed off. So you need to go 4 layers deep to go see, I think it was digital rights management action script was the 0 day there. You got to unravel all these layers to get to that component, that core component of it. So that's one of the first things we do. We take these document carriers and we explode them. We take out metadata, we take out embedded content. We recursively descend into those as well. We'll extract embedded logic. We'll do some normalization on it. Do some decoding if we find common encoders or common like string obfuscation. We'll also pull out the semantic layer. What's in the layers, what's in the document, what's in the cells of the spreadsheet. If there's an image embedded in there, is there any text in there? Well, what does that say? Pull that out. What's the metadata on the images? Every single object that is embedded in this thing has to be taken out and strewn across the table for analysis. This is all static. The next thing we can do once we have this all thrown out on the table is we start looking for IOCs, for example, IP addresses, domains, and URLs. There's other things like, for example, Adobe XMP IDs. That's something I'll cover in a second. Perhaps we pivot on our own alert labels or AV labels, right? There might be some commonality between samples. Perhaps the graphical lore is reused in multiple places, and visually we can see that although these 10 samples have completely different hashes, they are clearly the same based on the fact that the image lore is the same. As an example from a 50,000-foot view of what this might look like, this obviously you're not going to discern anything from here other than the concept of the scale of what this kind of pivoting can do. Because if you mix the two, file pivots and infrastructure pivots, now suddenly, if I have a file that references an IP address that maybe resolves to another domain that had another sample that spoke to it, I can draw the connection between these and put them into the same cluster. One of our goals here is if we can collate everything together, then we can focus on the outliers. But until we're doing that, we're just looking at a huge mound of data. So this pivoting is something we do manually that allows us to draw relationships and extrude entire collections of samples out of this mound of data, right? We're trying to do the quickest thing we can to plow through and find the interesting stuff. So I mentioned pivoting on XMP IDs. I want to dive into this one a little bit more just because it's something that's fairly underutilized, we'd say. There's image-based like perception hashing you can do, like A hash, P hash, W hash, D hash on images, but that's slow. Of course, the cryptographic hashes, 1 pixel change, it's suddenly a completely different, it's a completely different hash on the other end, right? So Adobe has this concept of extensible metadata platform. Really what it is either GUIDs or hash values that are designed to track parent to child relationship and revision tracking. So you have like the original ID, the current document ID, and the instance ID. And what's key is that these IDs are stored within the asset themselves, and they're updated within the asset as soon as the user hits save. How this visualizes, we'll have 3 different documents here. I got the blue line, the pink line, and the red line. The original is the blue on the top left. We made a copy of it to get to the pink column. We made another copy of it to get to the red column. Every time we save it, you'll see a new instance ID. And so what this allows us to do is pivot potentially on images that have left this embedded in there really, really rapidly. To date, I think we're tracking something like around 2,500 different XMP IDs. As we see them come out, it's a very, very low cost way for us to just suddenly put a pin on that entire campaign for every single new lure carrier that they make. Ooh, the formatting there did not come out correct. So, now that we've covered kind of, the thought process, what's working for attackers, what defenders are doing, and the stated problem is how do we go through this data? And the question, of course, comes, well, what is your data? In our case, My primary research is looking at carrier documents as they're strewn across DoD environments, right? The primary customer base for us is in the federal sector, and I'm very tuned in on their specific kinds of problems. A lot of enterprise customers in the more mature side of the SOC environment, they'll also be looking at things, at this level. I'd love to hear about other like file-related situations in folks' enterprise environments. So please ping me on the chat. And I also left contact information there for email, Twitter, and all that as well. I'd love to hear about people's specific problems. But for the data set that we can all publicly work on together, we look at virus total intelligence. Right, this is Google's purchased company from many years ago, very heavily used by most defenders. People purchase virus total intelligence to consume it on the back end, and then it's just an open system for folks to upload files from all over the world. And what we're looking at is a very recent statistics with regards to what the daily uploads to virus total look like. Forgive the formatting here, but that top line across is how many total files a day, followed by how many of those are distinct, so non-duplicates, followed by how many of them are distinct and new, so it's the first time they've ever been seen, never been seen before, followed by how many of them have at least one AV detection. And virus total's got something like 60, 70 engines now. So numerically, we're looking at every single day, there's about 400,000 at least potential malicious files that are coming into virus total. Someone asked on the channel about using Cuckoo to help speed up analytics. Absolutely. But you're not going to cuckoo, 2 million samples a day. It's just impossible to do that. One of our goals for wading through the noise for clustering things, for example, is then maybe we can go sandbox one sample as opposed to 1,000 and pass judgment on that whole 1,000. So dynamic analysis, 100% is there is certainly no the cost of sandboxing at that level. I'm just laughing about a comment in the channel. It is a high barrier, high bar to jump. So that's one of it's certainly one of the tools, right? There's no silver bullet. You throw everything in the kitchen sink at the problem of discovering a badness. Ooh. So if we look at the file distribution, no surprise, number one file type is executable, but we are interested in those non-executables. The biggest one is PDFs. That's about a million. We look at Office documents like 50,000. It goes down from there. So fairly big amount of data to deal with. So first things first, what do you do with reducing the volume? Like I'm not going to look at all these samples every single day. We've published a set of UR rules, our hunt rules, that reduce that set down into what ends up being about 5,000 samples a day, or less than 1% of the total daily corpus. And you can see some of the stats on the right-hand side. Those rule names all map to some open source hunt rule that we have published on that repository. All right, so what we're looking for is all these different layered carriers. And that graph across the bottom, color-wise, it'll match the legend above. The peak of that is at about 5,000. I know it's hard to read. So you can kind of see how it goes over time. We've built a system for ingesting all these things. I won't spend too much time on this eye chart, but the system is now open for folks to play with, and we'll cover some of that in a second. So, now that we've reduced the overall set from, a couple hundred thousand samples a day to a couple thousand samples a day, how do we take it down one level further, right? If we're looking at things that have very low or no labels at all, no AV detection, no consensus across the AV community, one of the things I like to look for that provides value is evasions that would not be done or not happen through any kind of point and click interaction. It's somebody has gone into the file and they've done some editing, some manipulation of it. While of course there will be some false positives here, the vast majority of them will fall more towards the something is suspect about it side. Some examples of that are MIME evasions, right? Like RTF files, for example, the Windows built-in rich text format. The MIME magic says that it must start with RTF1, but that's not the reality. It can just start off with open squiggly bracket back whack RT. The Microsoft parsers are notorious for being very flexible. If you look at, there was a tiny PE challenge once where folks were making this. The challenge was what is the smallest possible executable file you can make in Windows that will actually run? And it was a fun challenge. Folks were kind of passing it back and forth between one another. And it's quite amazing at how much they were able to bend that file and still have the Microsoft parser handle it just fine. Another example is PDF magic not being at 0. That can float anywhere in the first 1K of the file. And that gives you the opportunity to even do things like mime trickery. Perhaps I put something that starts with a zip magic, has a PDF extension. The PDF header is somewhere in the first 1K, and then the defensive stack thinks it's a zip file, tries to unzip it, fails. This hybrid file then gets over to the end user, they open it up, and whatever my PDF payload was will go to them. Another way that you can, and when I say burning your wares, I'm talking about from the perspective of the attacker, right? These are things that I would never do if I were making my own malware campaign. Another really silly one is you'll see, because we'll do things like, we're extracting macros from documents, ActionScript from Flash, JavaScript from PDF, and decompiling Java from the Java applets. Sometimes the attackers are very friendly and just burning, burning their campaigns by leaving symbols in their code. Things like shellcode, exploit, heap spray. If we see one of these, that's immediately going to be an eye catcher. Another example would be a UTF-8 byte order marker, right? Like you can start this at the very start of a file, and for a bunch of different security tools, you might break their MIME detection. And this is a technique going back to 2013. Another one, we call it chaff. This is just like wasted, like husk, just unused things. And visually, here is an example. What I've done here, this is an XML file. It's from a Microsoft Office, the 00 XML format. So, the zip file with the XML inside of it. And this is an exploit for what's known as the Microsoft DDE vulnerability. This thing was great when it first came out. I mean, I could literally teach an audience how to exploit this vulnerability with like 9 seconds and 3 clicks right from within a document. It's just a straight up command execution from a Word document. And so, very, very quickly, as we started seeing folks evolving on the tactic, this is a real world example that came out, and there's a great example of chaff. I've written a very, very tiny regular expression there that is highlighting, and therefore it's highlighting all the chaff, and therefore what's not highlighted and stands out is the actual payload. What we're looking for here is, that's the regex, we're just looking for all the XML tags, and then we can see the individual components. Here's this DD auto, it's pivoting to command.exe, and then from there going to whatever the next either PowerShell or pulling down some next stage payload. Right, so this is a great example of they use this tactic to try and bypass detections, but just the fact that they're even using this tactic allows us to detect that something nefarious is going on. It's odd for there to be this kind of just junk data in there. So by looking for chaff, by looking for purposeful junk data, superfluous bytes, we're able to potentially find something that someone's trying to hide, right? And that, from a attacker's perspective, that's just a foolish thing to be doing. You don't want someone to see a shiny box. You just want to be a needle in the haystack. But again, if they're going to make that mistake, why not leverage it to detect that that campaign? A more nefarious obfuscation type is, I call it the RTF byte nibble. This was discovered by Kaspersky researchers in like a February or something of 2018, and then later that year, a couple months later, that same technique was used by a 0-day in the wild campaign. So 2018 8174 was a 0-day in the wild that, if you had read Kaspersky's research on this byte nibble evasion and written a detection for it, this 0-day would have just fallen into your lap when these folks used it. And how it works, they essentially found very, very neat. I recommend checking out the paper. They found a flaw in the state machine that allows them to specify a byte sequence that ends up nibbling some data after it. So here again, I'm using a regular expression to show the before and after. What's highlighted is the junk bytes, and what remains is the actual content once the RTF parser goes to work. You can see that this obj data with this 0105, I see that, I'm like, all right, there we go. We have an embedded, some embedded content there. But with on the left-hand side, with the chaff in there, if you are looking at things from a static string perspective, you're going to miss that. Where are we? All right. So these are all the manual things. How can we now take this to the next level with automation, right? We've taken a big corpus of data wherever we've gotten it from, we've narrowed it down, and now we want to essentially find the individual clusters, the samples that are nothing more than instances or individual instances of the same core campaign. And we want to get those off the table and get them out of the way, right? This is the cosmic microwave background radiation of just all the campaigns that are going on, globally. If as defenders, we lean so heavily on IOC exchange between everybody, then you want to find the IOCs that are specific to you and your environment, not just the ones that are problems for everybody. On the ML side, what it comes down to is you've got your data, hopefully labeled data, and you need to choose your features that come out of that. And from there, you can you choose and pick algorithms to work on top of it. That's the fundamental 50,000-foot view, right? And so the models I find are primarily driven by the features that you select, right? And this is really sitting down with a researcher who's been doing this and trying to get the way that they think written down into a series of however many features, right? In our case, we have about 150 features that we extract from these document carriers. And the way that we split them, or at least the way I visually think about this, it's about a 75%, 25% split between what is a visual feature. So think about like when you just glance at a piece of code and in an instant, you know that it is malicious just because it looks heavily obfuscated from the structure of it itself. Again, this is foolish to do this because ideally you want to hide your payload in a large haystack of just normal looking data. But again, why not leverage this capability to identify the malware? Plus, the way they do the obfuscation is going to essentially allow you to cluster these things together as the same type of campaign. So think about things like the average length of the line, the number of defined functions, the number of defined variables, things like the gibberish. We have a gibberish detector for a variable name, like how many variable names look like they're gibberish. You just start sitting down and writing these things all down, and at some point you end up with a nice long list of features. Now, on the tunable side, once you've picked and chosen the correct algorithms, while the tunables take some more art than there is science, they can quote unquote be fuzzed as well. In this day and age of cloud compute, when in doubt, you can just brute force it and find what set of parameters, what set of tunables work best for that specific campaign or whatnot. So, going to talk about a couple of different things here. All right. Give me 1 second. I'm missing a slide. So let's talk about bag of words or BAW and what's known as term frequency inverse document frequency, right? If we're talking about the semantic layer, so when I'm looking at features of like a macro, for example, visually, I can write all those feature extractors, like, count the number of lines, count X, count Y. If you want to just be generic and just take the actual like words of the macro itself, what a bag of words is essentially you take that sheet of code and you just pick it up. And so all the different unique words are just jumbled together in one big bag. Here's your bag of words. Each sample, it can be seen as one bag of words. And then per sample, if you find terms that are essentially unique to a document versus the corpus of documents, those become interesting anchors. We use this tactic sometimes to find unique strings to help in signature generation. But you can also use it just to cluster things together as well. So just quick background on bag of words and TF-IDF, right? So now we've got our inputs. We've got a raw macro, which we will convert to a bag of words and then process with TF-IDF. And then we also have our feature vector. So we have two that was extracted from the macro itself. And then from there, we have different ways of doing clustering. One is looking at the macro itself and using fuzzy hashes like SSDeep and TLSH. Another is to use a machine learning clustering algorithm, probably the most popular of its kind, K-means. And that can be done on top of both data sets. So we can run it on, we can cluster our samples using the bag of words as an input. We can also use it, our features, and we can compare and contrast. Finally, and I have them on the same line because fundamentally they are the same general approach, is DBSCAN or optics. And again, this can take either type of input, either your bag of words or your features. I am very much a visual person, and so I like to I'll quickly run through like what these look like, the two fundamental different approaches for the ML pieces. First, on the fuzzy hash side, what is a fuzzy hash? Technically, it's a context-triggered piecewise hash, CTPH, right? SSDeep is the most ubiquitous option. It's actually SQL queryable, which is really rad. I mean, you can write a SQL query literally to tell you, show me all the samples in the data store that are within this distance of mine. That was very cool research. I'm drawing a blank on the name of the guy who pulled that off, but someone I'll put in the channel after the fact. A newer option is TLSH. So this is essentially a min-hash implementation from the Trend Micro guys. It's a newer option. It's gaining traction. It was recently included in Stix 2.1, and it appears to have some more vibrancy behind it. So certainly worth keeping an eye on. And why not try both? In both of these cases, the input's going to be raw macros, and we're going to have to choose some threshold for what do we consider underneath this threshold. It's going to be part of the same family, and we can put this both of these algorithms to run and create our clusters. So here you have to choose what is my threshold for clustering. That's a tunable. On k-means, the general approach, the idea is you are making an assumption on the number of clusters that there might be, which is a pretty big ask when you're dealing with this problem, obviously. This is why we're doing multiple approaches. And again, you could somewhat fuzz this. You can run this multiple times, grid search with different inputs and see how the outputs come out. But generally what you're doing is you're randomly choosing some points. You start measuring the distance between that dummy point and all other points, and then you move to the next denser area. You keep doing this until you're no longer making improvements. And so visually, we can see this as, this is 3 clusters here. That was pre-chosen. And as it moves, you can see that it starts to resonate on, this is 14 iterations in, and it's finally found its 3 independent clusters. The other way of going about it, and again, we'll see this in a second visually, it's a totally different method, is this DBSCAN or optics. The major difference between them is how it's going to handle your data. DBSCAN is better suited for uniform density data. Optics is better suited for varying density data. And you'll see where this is going to make a difference in a second. Here, your choices are 2. You have to choose what's known as the epsilon value, and you have to choose what your min points threshold is. Fundamentally, the idea here is we're going to choose a point. We're going to go an epsilon distance out. And if there's enough points in there that suffices the min point, then that suddenly becomes a core point. Otherwise, it's an edge point, and points without any neighbors are just noise. They're going to fall off the side. So again, visually, we can see it goes, 1, 2, 3, 4. Instead of choosing clusters and migrating them, this one is more of a start somewhere and kind of like infect out. Like you can kind of see it spreading. So here we've got a blue dot, and it starts to find its cluster. Later on, you see a green comes onto the scene, and then a red, and then so on and so forth until it has gone through and identified all your different clusters. Looking at the results, and so this is still a work in progress. We will open source this entire corpus. It consists of 10,000 unique recent carriers, both benign and malicious. About 20% of them are labeled. By the time we get it out to the field and to the open, it'll be a lot more than that. But using these tactics, just to compare them between each one, the idea is let's go cluster on using each algorithm. Let's take our data corpus and let's cluster them. If a cluster is labeled very heavily towards malicious, then perhaps all the samples there are malicious. And conversely, if they are benign, then perhaps all the samples in that cluster are benign. And so if we look at the potential label contribution that this kind of expansion gives us, and of course the accuracy is still in question. For example, SSD for sure is going to have some false positives up there with that massive add. But each one of the most interesting things about this is that there's not that much overlap, right? So the combination of them all adds up. Any individual one goes up to a max you see of 10%. But all of them together actually go up to almost 20 points in additional labeling that's plausible come out of it. So, what's left once you do all this? Well, you discard the clusters, right? And so what is remaining is going to be the things that you're going to be looking at through dynamic analysis, throwing it on your sandboxes, especially if you're going to be doing it on bare metal. If you're looking for samples that are going to try and be sandbox aware and perhaps use some tactic that, bypasses the anti sandbox detection. Manual analysis, perhaps focusing on the things that are deemed potentially suspect, but undetected. So there's not, it's not pulling up any AV labels, not triggering any alerts. Other things you can do once you've gotten to this layer is go back to manual. So now what's left, I might start going through them and find unique constants or assets, metadata. If we have access to how we got that file in the first place, perhaps we can find some commonalities in the network headers to further tune and cluster what's remaining. Again, with the overall goal being, we started off with 1 million. We want to get down to, per analyst, maybe a dozen a day of samples to look at. Just as an example, one of our most commonly very successful finding new malware campaigns is it's non-exploit based ones. You have to convince the user, coerce the user through some social engineering to enable your active content. So by pulling all these image assets out of carriers, running them through optical character recognition and looking for that, coercive vernacular, we're able to start finding very interesting low volume detection, but unique samples. And here's just an example of, the past couple of weeks worth of images that we've pulled out of that harvest. I know I'm running out of time, but just want to leave you guys with labs.inquest.net is where we're pushing all these things out. There's samples that you can search through, has an open API. There's IOC aggregation from various sources that we follow. We do reputation aggregation as well. And so, these are all the data sets that we've had to put together to get all this to work. And so we've tried to open up as much of it as plausible for our peers to be able to research as well. And that's it. I've opened up to any questions from there, and please feel free to get in touch.
That was awesome. I knew it was worth keeping up on you to bug you to do a talk. So it's a great presentation. We're going into a break now, but there was one question that someone DM'd me. They didn't want to post it for whatever reason. They didn't want attribution, but they say, given your background in research, do you find that applications like Microsoft Office Suite and browsers are riddled with bugs due to using low-level languages? Where do you see malware and exploitation going after safer languages are used like Rust? And is Rust going to unhack the planet?
We'll see adoption. There's been many new languages that have come out over the decades, yet most enterprise software is still written in things that we are familiar with, these unsafe types. It's the biggest difficulty is the complexity of the code. Just look at the attack surface, right? Microsoft Office, from what I've seen, is like tens of millions of lines of code supporting decades of features and a super, super rich environment. Like your browser, for example, will be one of the last places for vulnerabilities to die. You've got mixed media, a scripting language, all sorts of capabilities and attack surface that's not only rich, but constantly changing as well. So I think that the cat and mouse game will be on the client side for some time, especially when you look at, outside of the safety of the language, there's also the exploitation, just based technologies like your ASLRs, your DEPs, your safe SEH, et cetera. You really need access to a more rich environment to make exploitation easier. So I think that'll probably be client side will probably be the last place for vulnerabilities to die.
Great. Thanks again for the presentation. And please do fill out the evaluation for Pedram, and he'll be over in the Slack channel. If you do have questions, please take advantage of that. Also, I just got word that if you do fill out an evaluation, Sam's is going to do 2 random drawings for a $50 Amazon gift card. If you do put your name on it, you can still do it anonymously. Then you won't qualify for the gift card, of course, but just know that they are offering those 2 free gift cards. So we'll take our break now and see you in a bit.
Thanks very much, guys.